yesterday we have not this one. Yesterday we came across this paper which is authored by Joseph Ura. He revisited the winter bracing approach, and he proposed he visualized the behavior of the brace, of which the initial imperfection is included, which is more realistic than winter's bracing, because winter's bracing, it is very difficult. Well, it is all ideal, so the bracing stiffness is ideal, the bracing force required is also ideal, and that makes it difficult for engineers to believe which or to believe is it going to be good enough for the design, and where should be the number for the design in the real world, because you will not get the perfectly straight column and perfectly straight beams, or how will that be accounted for. And Joseph Ura has authored this paper, and he proposed the way to look at this problem by looking at the relationships between the load developed in the column versus the lateral deformation, and that tells you about the deformation overall. Let's say the deformation of the structure, which is the response of the structure. So the structural response shall be maintained, shall be limited, and we do not want to have very large deformation in the structure in order to mobilize the full capacity of the column strength. So the comparison has been given between the case where the brace stiffness is just right at the ideal brace stiffness, and you can see that the response of the structure is quite not satisfactory, because it cannot reach to the 100% loads, whereas the displacement is really large, like it could be as large as 10% of the original length of the structure of the column. So that number is huge in reality, and for sure 10% structure is going to damage, many things going to damage. So the brace stiffness has been increased by 2 times, by 3 times, and then you can see a really large improvement. So the line from here goes to there and goes to the to the 3 times the beta. So the deformation or the lateral displacement is minimized by just changing the stiffness of the brace to be just twice as much of the original beta I. That is much better to get much less displacement response in order to achieve the 100% load. So it is about 2 times, 1 or 2 times greater than original delta naught, and you will get the full bracing conditions. That means the full load is mobilized from the column. And the other aspect is about the bracing force. And the bracing force we are talking about, we can plot the relationship. So the first line again come from the ideal brace stiffness. When it is provided to this number, you're gonna need quite a large bracing force in order to maintain the structure in place against the collapse. So the bracing force is as much as 4%, when still your column is just having the strength of roughly about 90% of the critical load you expected. and it's gonna take like a lot more in order to achieve to some number which is close to 100%, which is not making any sense. If you just increase the stiffness of the brace, you can see that the behavior improves quite a lot, so you do not need much force to brace, and you can get 100%. Alright, so the stiffness of the brace always improves the behavior, and you add more stiffness, of course you get even better. But after the 0.3 beta I, you can see that this is the infinity. So this is the 3, this is the 2. So from here to infinity, it is not quite optimal at all, right? You can see this very far away. Okay, this is 1.0. So from 1, once you jump the stiffness to 2, you can see a large reduction of FBR from that point, and then from 2 to 3, the reduction is not as large, and from 3 to infinity, it's not that large at all. So you can see where you gain a lot. It is the optimal gain. Somewhere here and somewhere here is the optimal gain. But to come to here, you spend a lot more resources in making the brace, but you don't get much more in the saving of the FBR. So the number should be somewhere around this vicinity. Just like the deformation, from somewhere there, you have a lot of increase of the reduction. You have a lot of reduction from beta I and to 2 beta I, but from 2 beta I to 3 beta I, you don't find it that much, and from 3 to 4 to 5, okay, it's even less and less and less. So you cannot feel the benefit, and that is the wasteful activities. So that was what we have seen and what we understood from yesterday. We developed it. We go through the detail of the curves, how the equation was obtained, and this is about this page here and this page here. And it is not listed out in that detail, so you're gonna find a hard time understanding or drawing this up from the original paper. But with these 2 pages, I think it's gonna make your life much easier. And then we look into these pictures, and I told you that it is possible to do this using the buckling, the geometric stiffness matrix analysis program, structural analysis program that we have developed it in Octave. So you can do this, okay? You can try. The code is given for you already, so you can try this case and more and more and more, so you can have like even more number of brace, and the configuration of brace could be different, but it's gonna take quite a lot of effort to do all of this using the theoretical and approach. So you're gonna deal with a lot of equations. Well, it is still bearable, but it is much easier to go this way, and you will be capable of playing with many things, many possibilities, rather than just a simple setup like in the paper. And then The end of this paper, in of Yura's paper, is about the case where you have the A1 and A2, the brace is going on, is attached over here. What's going to happen? What will be the ideal brace stiffness, or what is going to be the good brace stiffness to make sure that the system is well braced and be able to mobilize the full capacity. And the program that I give you also can handle this situation. So you got to make sure that you discretize the node at the middle of these two segments in order to enable the buckling. Okay, so that is possible by the program, and life will be much easier. You can find the right number, the appropriate number for your calculation. If you want to make it conservative, then you can pick up you can use this upper part to control the spring stiffness, because the A1 is shorter. That's gonna make the beta calculation more strict, and the PE, if it is obtained from the upper part and divide by the length, which is from this upper part, alright, PE is going to be larger, the length is going to be shorter, so that's PE over the length, 2 times PE over the length. That's ideal brace stiffness is going to be the maximum possible number it could be. But if you want the refined analysis, then just dump the number, dump the parameters into the code, frame buckling, and then you will get the precise number. Well, of course, you will incorporate the factor of safety later on after the calculation, because this is the calculation in the paper. You will need to incorporate the uncertainties that is expected in the real construction. Alright, so that is it for Yura's paper. It is very worthwhile. Just a short, not that many pages paper, but this is the fundamentals of the bracing design in the AISC specification. So I bring you to the appendix 6 in AISC specification. So this is continue from Joseph Yura paper. At least the figures provided in here is coming from Joseph Yura. So let's take a look at this all together, so to see what's in the code and how the paper is the backbone of the stability of by stability design using the bracing. So the code talks about the appendix 6. The equation in here is for the design of the beam bracing, column bracing, beam columns. For the truss, this is interesting for you. You will by chance bump up with the truss issue, truss design. So in the design of truss bracing, the compression cord may be treated as the compression flange of the beam. The beam bracing will be covered after we finish up the first part of this appendix 6. Okay, the beam bracing, we're gonna see another Joseph Yura's paper that is the fundamental of the beam bracing design in the AISC specification as well. It is kind of cool to have many of his work stuff in the AISC specification, and it will not be removed out of this because the knowledge there will not obsolete. Well, the techniques used for analysis for the brace stiffness estimation might be different from the past. We are in 2020. The paper was roughly 25 to 30 years ago. But the technique has to be changed. I just try to incorporate the nowadays technique that you can do to come up with all of these presented in the paper we covered. But we use the numerical techniques, we use the calculation tools that is more powerful than before. So we have more flexibility, we have more freedom to play with all of these stability issue. So you are not just sticking to the knowledge of the 1995 age. You are going to use the more advanced, the more should it be called more advanced? It is. Nothing is more advanced than any other thing, but this is more relevant to the business that we are doing, more relevant to how we do the business in structural engineering design. Okay, so general provision, the provision talks back, refer back to Winter's paper. The one that we read is 1960. The one that is purely about the experiments was in 1958. Okay, so Winters developed the concept of dual requirement bracing design. Okay, well, anyway, the Winters idea we know it already. Winters produced the ideal bracing requirement, DEAL, bracing requirement that beta equals to some number PE over L, and this starts from what? From 2, 3 point something, 3 point something. Okay, so in the question mark, it depends on the number of the bracing points you had for the column, and this question mark can be obtained using the code that I share in the Google Drive. Anyway, well, we come to here, and two general types of bracing system, panels and point bracing, available in the world for use. So let's take a look which one is panel bracing and which one is point bracing. Panel bracing, in the past it was called the relative bracing, and this point is discrete bracing. In the past code, but the latest AIC, which is not so latest, not so new right now, it is it is open to public in 2016. So this is 2020. Expectedly, they are going to issue the new code very soon, because this has been 4 years. From 2016 to 2020. In probably in 1 or 2 years from now, we might see the newer version. And once we get a newer version, then we're gonna look again. Okay, what has been improved from the past? But first of all, the panel bracing or the relative bracing. Why is it so called relative? It is the brace. You can see this bracing. This brace this level by controlling the relative displacement to the level below. So it is called the relative bracing. So the relative displacement between these 2 points will not be will be controlled by this given brace. Okay, and then this point and this point are controlled by another one, and the last one like this. So relative displacement between stories control. Whereas on the right hand side, the discrete bracing, it gives you the brace that is attached to the given point. So if this one move, okay, if the whole story move, then it is the absolute delta absolute. Previously it was the part that was controlled is the delta relative. And this one is the absolute. So you have the absolute compared to the overall to the original coordinates. This is just relative between 2 points. Okay, so there are two kinds of bracing system: the relative bracing, or so-called in the new code panel bracing. And the definition of panel bracing, it attached to locations along the column, the distance between LBR of the column. The panel bracing system shown in the figure consists of diagonal and struts, control, blah blah blah. Okay, I think my explanation covers the paragraph already, so we don't need to read through. And the point bracing is discrete. Only the point that it braces, and without direct interaction with adjacent brace points. So without direct interaction with adjacent brace points, it has nothing to do with the neighboring level. Okay, so distance between adjacent LBR, the point bracing shown. Okay, and this paragraph as illustrated in figure CA 6.1, the panel bracing system for beam often consists of, okay, for beam we will talk about it later. So the column is at the top, and for the beam lateral bracing, you have like this, the relative bracing. So beam is supported by this and this, and in order to control, to prevent the beam from sideway lateral torsional buckling, then the brace is given like this, such that it forms something like the truss mechanism to control the lateral deformation. And the torsional brace is also provided. Okay. Now let's see here. The bracing requirements stipulated in section 6.2 and 6.3 allow for the member to develop maximum load based on effective length, LC and LB, taken equal to the unbraced length between brace point. The bracing requirements in 6.2 and 6.3 generally are not sufficient to permit development of member strength based on LC or LB smaller than LBR. Okay, that is development of column and beam. Okay, blah blah blah. Alright, this 95%, this is the figures we saw even from the yesterday. Okay. I think this part here is going to be important. In addition, this means bracing requirement to reach specific rotation capacities and ductility beyond scope. Okay, but this is important. The provision. Let us see. Okay, in this block here, this provision for column and beam respectively stipulated a required brace stiffness beta BR equals to 2 over phi, or 2 times omega for the ASD. 6.2 and 6.3. Okay. The two, do you recognize the number? The number 2. The number 2 come from not this one. The number 2 comes from this paper. So 2 is here. 2 times beta ideal. If you look into the 6.2 and 6.3, I do not want to jump there because it's gonna take time to jump back and jump forth. But the 2 come from that. So you have the 2 times the ideal brace stiffness. No. 2 is the ideal brace stiffness. Sorry, the beta ideal is equals to 2 times PE over the unbraced length L. That's it, right? But the point is that 2 will be increased into 2 divided by phi or 2 multiplied by omega. The 2 divided by phi is the LRFD, and the 2 omega is ASD. So 2 times omega is going to be 4.0 because the omega has been it is given to be 2. It is a factor of safety in the ASD concept. So you have a factor of safety equals to 2. So finally, in reality, you're gonna have the behavior which is like this, because you have 2 and then you multiply by 2, so you get the 4 beta I. You're gonna have this behavior. So it is more conservative. It has less deformations and it has less bracing force. That's the way the code is made in order to just give you the more conservative design. If we come back to this one, let's see the LRFD. You have the 2 divided by the strength reduction factor, like the phi of 0.75. So divide by 0.75, you end up with 2.66. 2.67. Quite a big room, quite a big difference to the ASD. Okay. The required, but by the way, the number 2 again. The number 2, it is, let me grab the Winter's paper. Okay. So here, the number 2 is just 1 point. If you have 2 point bracing, you end up with 3. This is 1 point. 3 point, 1, 2, 3. Okay, so number will be changing like this. You'll be using this number in here from Winters, or actually the frame buckling, the frame backing close. If you do not have 1, 2, 3, 4, it turns out to be 5, it turns out to be 6. You can use the code to find. I think you used to see something. I'm not sure exactly, but they used to propose something. Okay. Now the required brace strength, PBR. We used to have the FBR in the paper by Yura. So here he used the FBR, but here is the PBR. Okay, so PBR is a function of the initial out-of alignment, as I showed you yesterday. Out of alignment of the brace point delta naught and the brace stiffness beta. The brace strength requirements are based on the nominal brace stiffness without the inclusion of phi and omega. The brace strength requirement. Okay. Separate resistance factors are okay. This is interesting and maybe good to cover a little bit. The brace strength requirements are based on nominal brace stiffness without the inclusion of this thing. Okay, so basically it said that you can compute the brace strength, and then later on when you design the member for the strength design, so you go to the chapter for the axial behavior. If the brace is carrying the axial force, that is an example. So you take this force, you do not include the phi and omega here yet, and this is the nominal strength. Okay, this is the nominal strength requirement, and when you go to that chapter is going to require you to apply the phi or omega at that place locally. So that depends on what kind of force that you expect. If the brace is carrying the bracing load through the flexures, then there will be the strength reduction factor for that regard. If it is carrying the load using the compression, that is going to be another strength reduction factor, something like that. So this part here will be later. It will be applied later. Okay, if you do it here, you're gonna end up with like the duplicates, phi and omega. So you're gonna get like too much strength due to the duplication of these two things. These two phi and omega. But that depends on your your design, if it is LRFD or ASD. Separate resistance factors and safety factor are applied in the design of bracing system component to resist those forces. Okay, fine. Now, for the panel lateral bracing system on a column, the relationships between column load, brace stiffness, and sway displacement is shown in this 6.3. Okay. And this 6.3 is the figures that we saw yesterday. I showed you this figure yesterday, but the only difference is about the picture of the bracing, the brace column there. So the picture I showed you is this one, whereas this one is just half of the picture that you saw. Okay. Come back here. The relationship between column load, brace stiffness, and sway is shown in this figure. If the bracing stiffness beta is equal to the ideal brace stiffness for a perfectly plumb member, beta I, the displacement of the bracing system becomes large as P approaches PE. Okay, such large displacement, okay, I explained that already. For the panel bracing system, use the beta equals to 2 beta. The assumption of initial displacement results in bracing force equals to 0.4%, and this 0.4% of PE is mentioned over here, that it used to be going like infinity, but once you increase the brace stiffness to 2 beta I, you just finish everything up at 0.4% of the PE, which is very small, 4 in 1,000 of PE, right? That's very small value. The foregoing LBR is the distance between adjacent brace point as shown. Okay, just the definition. And delta is relative lateral displacement. Okay, we know of that already. Now we come to this point. So delta naught is given by the LBR over 500, which corresponds to an erection tolerance equal to the maximum frame out of plumbness specified by EISC code of standard practice for steel building and bridges. So the standard practice for the erection is giving you the room for the error, which is less than LBR over 500. That is 2 in 1,000. So if we think about 1 meter length, you have the error, room for your error, which is 1 meter is 1,000 millimeter. So you have 2 millimeter tolerance allowed by this erection specification. And also the ASTM requirement for the production of the steel cross-section, commercial cross-section, you are subjected to the requirement that the out of straightness, initial out of straightness from the factory shouldn't be greater than the number which is LO 500 or LO 1000. I'm not so sure about that number. I don't remember exactly, but LO 500 here is going to cover everything. So something there, let me see. As shown in and there is relative lateral displacement of the brace from the plumb position caused by erection tolerance, first order effect, gravity, load, etc. Okay, but it's not talking about the load yet, the load in the brace yet. Okay, this is gonna be important as well. For cases where multiple columns are being braced and it is unlikely that all the columns will be out of plumb in the same direction, recommend the use of an average initial displacement due to the erection tolerance of some of these. Okay, this is more detailed, but this part here, this deduction of delta naught is added with the first order effect causing additional out of plumbness. So here the bracing force is actually computed from the first order effect. So what is this first order effect? The latter part here you will obtain from the stability point of view, right? But the first order effect, that means if your structure like this is braced, and this bracing is for two applications. First of all, it enhances the stability of your structure. Second of all, it will be used to carry the lateral force from wind, from earthquake. This from wind or earthquake, this is the first order effect. And the stability issue is this one here. It's a second order effect. So the design of the brace, the strength of the brace has to be greater than the combination of the first order effect adds up with the second order effect. Okay? You cannot just design for the stability point of view and without considering the effect from the externally applied load, which is the first order. Okay, and everything is defined down here. Let's see. Okay, panel bracing contains first order shear force and factor that can be applied. Okay, all right. Here we are going to jump back into the literatures, which is again provided by the Joseph-Ura. Now we are going to talk about the bracing in the beam system. So again, we will go through his literatures, but I think that it is not necessary to go through the very fundamental part or the introduction part of this paper. This is a paper named Fundamental of Beam Bracing, Engineering Journal 2001, so almost 20 years. And he talks about the bracing for the beam, of course, and the introduction was about the column bracing that you have seen. Actually, the beam bracing adopts the idea from the column bracing, because the beam bracing, the problem that you have from the beam bracing is from the lateral torsional buckling, and that lateral torsional buckling is controlled by the top flange of the beam. As the top flange of the beam, if you think of the simply supported beam and you apply the positive bending moment to the beam, top flange is under compression, and the part that is under compression is going to lose stability, right? The tension side, which is at the bottom, is not going to lose stability. So the idea, the concept of the beam bracing is to provide the stability to the part that is prone to the problem. So Ura talk about his paper. He elaborates on the things in the previous paper. Okay, so that's fine. We are not going to cover that, but we're gonna come into this thing, lateral bracing of the beam. Just right away, so we skip all those things we cover already. This paper is actually used the numerical technique for the study. He also has the experimental works done in parallel with the numerical study. Okay, but as the cases that were studied was a lot, the location of the force is changing, the location of the brace is changing. There are so many parameters that are varied for this study, so it is required that the numerical tools was used for the study. Okay, so Let's see. First of all, the uniform moment condition in the basic case for lateral buckling of the beam, right? If a lateral brace is placed in the midspan of such beam, the effect of different brace size is illustrated by the finite element solution for this size, and this span long in figure number 6. Okay, but we will come down to the figure in a bit. For a brace attached at the top, the beam buckling capacity initially increases almost linearly as the brace stiffness increases. If the brace stiffness is less than some number, the beam buckle in the shape resembling half-sine curve. Even though there is a lateral movement in the brace point, the load increase can be more than 3 times in the unbraced case. Right. Ideal brace stiffness required to force the beam to buckle between lateral is okay, 1.6 keeps her in. Okay, let's see. Yeah. First, we just talk about this case. If you have no brace, 2 axes. One is the brace stiffness, so it is not like the graph we had before. This is the increasing brace stiffness, and this is the capacity. So critical moment and refer to the moment with NOBR is the no brace condition. Okay, this one, no brace. So without the brace, without the brace, the capacity is identical to the no brace condition, so it is 1.0. So basically, this study has to be conducted on the beam with the uniform moment, and the span is fixed, and the brace is lateral brace, like this. Okay, 20 feet, which is 6 meters. And this number, this number, the stiffness is varied, and no brace condition is without the brace. Okay, just that. So the paragraph above talks about the no brace condition, which is used as the reference, and this one, top brace. So the brace is provided and it is attached to the top flange. Here is your Y flange cross section. So the top flange is braced, so the lateral deformation is minimized, and when you achieve to the ideal bracing stiffness, then you can mobilize the maximum. Okay, it come back. Okay, we get the connection problem, but it come back already. So you come to the ideal brace stiffness, and you can fully mobilize the capacity of the beam. That is what given in the first paragraph there. If the brace stiffness is less than that, even though the lateral movement increase more than 3 times of the unbraced length, the ideal brace stiffness required for force and buckle 1.6. The number 1.6 is is this one 1.6. It is less than 2. It is halfway. Okay, but in this graph you can see that we have other things. So theoretically we prefer the top flange brace compression flange, in other words. It is a compression flange. The word top flange might not be clear. Let's call it compression flange. So you are not going to do something dumb like only brace the top flange, but you are in the situation of the cantilever beam that the bottom flange is under compression, but you brace the tension flange. That is a bad idea. Okay, so call it compression flange. The point is that if the stiffener, if the brace is applied at the different place, so it is right at the centroid of the cross section. When it is right at the centroid of cross section, the rotation is not well prevented. It is not as efficient as the case above. But anyway, the top flange or compression flange is still restrained by the brace, and you can see that the behavior looks like this. So it takes you more stiffness from here to there in order to mobilize the full moment at the buckling, but still the full moment, this ratio of MCR being something like 3.xx, okay, can be mobilized. But the worst case is from the case where you brace at the bottom. So this is terrible because compression here, tension is here, and you are bracing the part that is not problematic. The problem is in the compression. You lock. Oh, this is also sorry. This is also the centroid. Sorry. Oh, sorry. Centroid. Oh, I just talk about. Sorry. It is between this and this. We have only just a centroidal brace and the top flange brace, no bottom brace, but the centroidal brace, we have two different cases. The case where you have the stiffener. The stiffener is preventing your, well, as I explained you already, that the centroidal brace is not effective as it is not locking the compression flange. But if you add the stiffener in, you still can mobilize this moment. But without the stiffener, you will not be able to mobilize the moment as the brace stiffness is increased drastically, but still you cannot achieve to the required load. And the reason is about the help from your stiffener plate that prevents the distortion of the cross section. Your cross section cannot go like this with the stiffener plates. So no stiffener, you have worse behavior. With the stiffener, you still can mobilize the load, but you will prefer the one with the top flange brace the most. Well, you might end up with a situation that you cannot achieve, not be able to get the compression flange brace. Anyway, that is possible. For this, picture factor that affect the brace stiffness. Okay. Next. Any brace stiffness greater than this value does not increase the beam buckling capacity, and buckle shape is full sine curve. Okay. They just talk about the picture there, and no matter how much you increase the brace stiffness like this, once you hit the limit, then the brace will not increase the strength of the system anymore, because it is going to be controlled by the beam itself. Okay. When the brace is attached at the top flange, there is no cross-section distortion. Yeah, highlight this up. When the brace is attached at the top flange, there is no distortion, which is the key idea. And this is how the stiffener plates help increase the capacity of the system. No stiffener is required at the brace point, of course. Lateral brace placed at the centroid of the cross-section requires an ideal stiffness of something which is greater than before. This is the explanation of the graph. If no stiffener is used, substantially more bracing is required for the no stiffener case, because the wave distortion, and that's the wave distortion I showed you, I sketched to you before. The centroidal bracing system is less efficient than the top flange or compression flange brace, because of the centroid brace force causes the center of twist to move above the bottom flange and closer to the brace point, which is undesirable for lateral bracing. Okay. For the case of beam with a concentrated centroid load at the midspan, shown in figure 7. Let's see the figure 7. So it is a concentrated load. Previously it was the uniform moment, okay, MCR applied on both sides. Now it is the load at the midspan applies like this. So let's see. The moment varies along the length. The ideal centroid brace. Oh, by the way, this is the reason why the study has to be, another reason why it has to be conducted numerically, because the development using the closed form solution is very difficult. The case that the moment is uniform, you used to see in the development of the beam lateral torsional buckling capacity previously, right? But the case where you have the moment which is not uniform like this, as you apply just a point load, that is very difficult for the closed form solution, and it is much easier to go with this numerical technique. Okay. Moment varies. The ideal centroid brace is 44 times larger than the ideal top flange brace. For both brace location, cross-section distortion had a minor effect on PCR. The maximum beam moment at the midspan is 1.8 times. Okay. We have two cases, top flange brace and centroidal brace, and the behavior is so much different from before, as the effect from the brace is more clear at the top flange brace. The bending moment diagram for this case is like this. So you have the critical issue around this point, and that makes it more clear than the case where you have the bending moment like this and you have the uniform bending moment. So the point that is braced is helping, but not as much as this one that is braced right at the point where the peak moment is expected. Okay, so this is just for this graph. There is nothing more regarding this graph. Figure 7 was done. Now figure 8. Let's see what we had. Figure 8, look at the picture first. The picture shows the simply supported beam subjected to the point force acting at the middle, and we have different situations. First, we have top flange loads. Okay, the first one is really low, and this is the top flange loading with the brace at the centroid. So it is ugly. Centroidal brace. This is the worst. This is the ugliest case. Now, load is at the top flange. Now the load is also at the top flange, but the brace is at the top flange as well. So the brace is attached to the right point, even though the load is applied at the top. Well, the top load is bad. The bottom flange loading is the desirable situation, as we have gone through in the beam design, and you saw, if you recall, the CB values for the beam design, right? CB values is going to be affected by the location of the load, and the location of the load at the top is going to decrease the CB values, and the overall beam bending moment capacity is going to reduce. So the bottom one is the most desirable one. Okay, anyhow, the behavior shows that it is possible to achieve to the maximum load over there with the top flange loading and the top flange bracing. So this is important. If the situation is improved further, the load is at the centroid. So you can see that initial when the brace stiffness is 0, you still have the difference between these two systems. So the load at the centroid without the brace compared to load at the top without the brace, you get this gap, and this gap is caused by the CB. Okay, and you load it up, you can catch this load more quickly, so you do not need as much brace stiffness as the other case in order to pick up this level. But still, the counterpart one is not bad, but the worst one is the centroidal brace and the top flange loading. This is the worst situation that you can imagine. Okay, let's see what else that is explained here. So figure 8 shows the effect of load and brace position on the buckling strength and laterally braced beam. If the load is at the top flange, effectiveness is greatly reduced. We're not going to talk about number. Okay, let's just see the important part. Load position effect must be considered in the brace design requirement. This effect is even more important if the lateral brace is attached at the centroid. Okay. The result shown in figure 8 indicates that a centroid brace is almost totally ineffective for top flange loading. Almost ineffective means you start from here, you put the large brace stiffness and you do not gain more from this point. It is just very insignificant compared to the different point of the brace that gives you like, here is the 8, right? This is like maybe 12. So you have 12 over 8, that is like 1.5 times. But if you put the brace at the right point, you come from 8 to about 48. So it is 6 times greater by just placing the brace at the right location. So this is a very smart strategy, and it is a very important thing, because you do not want to brace ineffectively. That is your life, that is your career. So you brace at the wrong point, and you use the capacity of another one that is disastrous. So this is where you brace, and this is the capacity that you expect, the capacity in the design, and this is the real capacity. So structure will fall, and I told you that the stability is the failure from stability is very disastrous. So it fall without notice, it fall without warning. Once you reach the bifurcation point, it is just falling down very quickly. So you might be wrong by 6 times, like that, like in the graph that you see. So the location does matter, right? Make sure that you are not risking your career by just placing the brace at the wrong point. It is not just, I brace it already and it's gonna stay. No, you can be wrong by 6 times. From according to this paper, 6 times. Your situation might be different, but this is the magnitude that you can end up with. So the strength reduction factor is generally like the smallest one, 0.75, that around that figure, strength reduction factor. Or if you talk about the factor of safety in the allowable strength design, well, if you talk about strength reduction factor alone, it is not enough, because we need to talk about the load factor as well. But if you just think of it like the allowable stress design, we think about factor of safety, which is the combination of load factor and strength reduction factor. You have the factor of safety being around 2, and factor of safety being 2 will not be enough to cover 6 times difference, right? You still miss 4. You have 2 that cover yourself, but 4 more. Where would that 4 more come from? So you cannot find the source for that 4 more, and you'll be ending up with the problem and steel structure failure. Many times you might have seen from other courses that it is very dangerous. So be careful. Okay, I have nothing to say, but just be careful about this stability design. And normally this stability design is very detailing. The detailing means like the brace is going to be at the top, or at which location, is there going to be the stiffener. When we run the model, we run the analysis of the structural modeling. Generally, you just use line element. You are not using the finite element, having the shells element combined together, and you make the beam. Correct? That is not the situations that you will do, and maybe in a lifetime you will never do that. But the point is that the stability is very sensitive to all the matters that we are covering in this paper, so it will not be shown from the analysis program. In other words, in conclusion, it is not shown in the structural analysis program. But that depends on how you detail the structure, and if you detail it incorrectly, if you don't check the drawing that the draft guys made, and maybe attach things to the wrong place. Maybe he does not have as much understanding as you do, so he attached the brace to the wrong place, and then your capacity is dropping down a lot, and it just slipped through your eyes. You didn't see, you didn't aware that it is done in the wrong way, so you have a chance that your structure is going to be collapsing. Okay, then next, the results shown in figure 8 indicate that the centroid base is almost totally ineffective. This is not due to cross-section distortion, since a stiffener was used at the brace point. But the top flange, okay, so stiffener again is not going to help if you have the top flange loading. This is due to the distortion. Okay. So, stiffener, you introduce it in, it doesn't guarantee your safety. It is in the wrong case, then it does not help. The top flange loading causes the center of twist at buckling to shift to the position close to mid-depth for the most practical and brace length. Okay, whatever. Since there is virtually no lateral displacement near the centroid of the top flange loading, a lateral brace at the centroid will not brace the beam. Because of cross-section distortion and top flange loading effect, lateral brace at the centroid are not recommended. Okay, so I put the double star there to just, well, I think you can list all these things out. It is like we are going through just a paper, just a manuscript. But the point is that the information in here should be listed off. If you are going to detail the steel structure, you should list this off like a checkpoints, and then go through these checkpoints when you design steel structures and design for the stability of steel structure, especially for the brace. The point is that the brace is a very useful thing. It enhances the capacity of your structure, but if you don't do it in the right way, you don't get that effect, and then you overestimate your structure. And as you overestimate your structure, that's gonna make things collapse very easily, because of the capacity calculation is subjected to the very large error. It could be wrong by very high, very large error. Design recommendation will be developed for the top flange lateral bracing situation. Torsional bracing near the centroid or over the bottom flange can be effective, as discussed later. Load position effect discussed above. Assume that the load remains vertical during the buckling. Okay, that's the assumption. In the laboratory, top flange loading condition is achieved by loading through the knife edge at the middle of the flange. In actual structure, the load is applied to the top beam through secondary member, which might also move, or the slab itself. Loading through the deck can provide beneficial restoring effect, illustrated in figure 9. Let's see the figure 9. This is the restoring effect. So when the beam lose the stability, the lateral torsional buckling occurs, right? And when the lateral torsional buckling occurs, you're gonna see this so-called tipping effect. Tipping effect, it used to be like this, but then it tips over like this. So as it tips over, what happens is that this tips over cause you this moment arm. So the centroid of the beam is there. You have this moment arm, and force is concentrated in just one point at the edge of the flange. So this is going to create the restoring moment. So this moment is trying to push the system back into the previous condition, which is not buckle before the lateral torsional buckling. So it opens up, and then the moment is trying to close it back down. This is the restoring effect. But the point is that you might end up with this situation that the restoring effect, as you have the bending moment in this phase here, you might reach to the plastic moment of the flange, and then you cause the permanent deformation of the flange, and it looks like this kink. So this is the cross-section distortion case. We'll come back and see what else is discussed over here. So provide slab itself loading through the deck can provide beneficial restoring effect illustrated here. As the beam tries to buckle, the contact point shift from mid-flange, which is the middle of the entire beam, to the flange tip, resulting in restoring torque that increase the buckling capacity. This part is going to help push the system back. Unfortunately, the cross-section distortion severely limits the benefits of tipping. Well, if you have the stiffener, then the cross-section distortion is going to be minimized, right? Because the stiffener is going to control the top flange moment, and the moment turns out to be carried by stiffener more than the top flange itself under the bending mode. Stiffener is carrying the bearing mode. Linder and Smith developed a solution for tipping effect which considered the flange web distortion. Test data indicates that cross member merely resting on the top flange can significantly increase the lateral buckling capacity. The restoring solution is sensitive to the initial shape of the cross-section and the location of the load point on the flange. Because of these difficulties, it is recommended that the restoring effect not be considered in the design. So just keep it as like just a freebies. You don't use it. It is something free you can get to enhance the stability of the structure, but you don't really want to use this in the design, because you might end up with nothing with this, subjected to too many things, and you have more chance to be wrong. So that is risky in other words. When a beam is bent in double curvature, the compression flange switch from top to the bottom flange at the inflection point. Okay. Then we should call the compression flange and tension flange to just make sure that we to avoid the confusion. Beam with compression in both top and bottom flange along the span have more severe bracing requirement than beams with compression on just one side, as illustrated in the comparison of the cases given by figure 10. So let's see the figure 10. Okay, figure 10 is here. This is the top view. The beam is prevented against the rotation on both ends. Bracing is attached on the side, so the lateral displacement is prevented. This is how the beam is loaded. So point load is applied, and brace. Let me check. This first case is the brace attached at the top only. Oh, okay. This is just one single curvature case. These two are double curvature case. For the single curvature, where is the brace? Not sure. we got to read from there. But for the double curvature cases, two kinds of braces apply: both top and bottom, and the top brace only. So top brace only, you have just this much, about 1,400, 1,500, whereas the top and bottom bracing provide like 3,500. It is more than 2 times increase if you provide both, because you gotta have the requirement in the bracing of the compression flange at the top and the bottom, and this one just gives you just one only. But for this case, it is easy. I think this one includes only just the brace at the top flange, so it can go up to 3,000, but not as high as this one. Okay. Moment for no bracing, the buckling moment is the number of brace attached to one flange is ineffective for reverse curvature because the twist at the midspan is not prevented. If lateral bracing is attached to both flanges, the buckling moment increases non-linearly. The ideal value shown by the black dot. Okay. Greater brace stiffness has no effect because buckling occurs between brace points. The ideal brace stiffness. Okay. No more. Now over here, is this just the... Okay, now figure 11. Now we continue with the figure 11. So let's see, figure 11. It is the test, the simulations of the case where the beam is the simply supported beam subjected to uniform moments throughout. This is having the larger span. You have 3 braces, and this is just one. This is 20 feet, this is 40 feet, so only one brace point. Basically, the unbraced lengths are identical, so 10 feet and 10 feet for these two cases. And the case where you have just one brace and unbraced length 10 feet, it is given in the dotted line. Okay, so first of all, this is just a single curvature buckling, like this picture. So the flange, compression flange buckling into this shape, one half side curve. And once you achieve to the ideal brace stiffness, then it turns out to be one full side curve, not the half side anymore. Now it is a full side curve, of which the buckling, the L value is equal to 10 feet. So you have just one kink like this. Whereas the case here, brace stiffness is varying along this direction for both. For this one, multiple bracing points. So first of all, when the brace stiffness is equal to 0, then you have the larger unbraced length than that case, so you have the moment which is lower than that one. And then the brace stiffness is increasing until, okay, you come into this line. And come into this line, it forms the double curvature buckling, one side curve. But one span here is equal to 20 feet, which is as much as this case here. It is this shape for this one because this is total is 40 feet, whereas this one is the total span length is 20 feet. You come to one number, you achieve to the next level, you can form this buckling shape. Okay, but still the distance here is not 10 feet. It cannot form the like this one 10 feet. So the strength is capacity is still less than this dotted line. And until you get to this stiffness and you end up with like the 10 feet buckling buckling length. Okay, so this is the thing you observe from multiple bracing points. Let's take a reading of this part here. The bracing effect of the beam with multiple braces is shown in figure 11. The response of the beam with 3 equally spaced braces is shown by the solid line. Okay, this is just minor information. Before we come to the lateral brace design, let's see this one. This is going to be the last paragraph of today. Report the result of the test program on the lateral and torsional bracing of beams for comparison with the theoretical study presented above. Some typical test results show good correlation with the finite element solutions. Since the theoretical results were reliable, significant variables from the theory were included in the development. In summary, moment, gradient, brace location, whereas affect the buckling strength laterally braced beam. The effect of the cross-section distortion can be effectively eliminated by using placing the lateral brace. Okay, fine. The next part of this paper is going to be about the design of the brace and the bracing stiffness will be computed. This is something that I try to look up and just found here. So the brace stiffness is introduced here, and the brace stiffness, the P, is computed from the axial compression of the flange against the buckling. That is the idea for the development, and there will be other parameters involved in this brace for the beam. Okay, so many things gonna involve, and then the torsional bracing is covered, and the torsional bracing design framework is also given, and there's a bunch of things relating. So we will continue the next time. And actually, I would like to show you to use the program in Octave to demonstrate something in the previous URAS paper. But the point is that due to the simplicity we made for the program by just removing the displacement along the axis of the member, and that makes it sort of, how to say, it's gonna need a lot of modifications in order to run and to track the deformation versus the applied load, lateral deformation versus the applied load for the case where you have the initial out of straightness. I looked into this matter in the morning and found that I shouldn't simplify the code, because as it is simplified, then it turns out to be 2 degrees of freedom, and then I cannot apply the axial force in order to see the lateral displacement versus the axial force that I apply in the code that you already see. So I might do some sort of modification out of the class time. I will video I will record the video and then make it available on YouTube once I finish this up. Okay, so let me wrap up for today. We're gonna meet again for the steel structure in the next week, and this is the class number 26 already. I think next week could be the last, probably. We are pretty much covered. We have almost everything. Okay, if we just go through the octave a little bit more to play with the buckling and deformed shape, buckling shapes, which I try in the new code here already, but the plotting subroutine is not working satisfactorily for me, so I will try to find if there is anything. This plot, deformed shape plot, is coming from the last semester at the end of the year, that after the class, after the final exam, we developed the deformed shape plot subroutine, but something is not going right in this problem, so I'll find what went wrong, and once it is cool, then we can plot the buckling shape. The eigenvector is already correct, there's nothing wrong, but it's just a matter of fact that the plotting, the tool that is used for visualization, is still not working correctly. So just that. Okay, all right, you guys have a good day. We're gonna meet again in the next week. Bye bye.